Today's topic is SDN-enabled optical circuit switching for data centers and metro networks. I'd like to start by talking about data centers. There's a couple of reasons. First, because the need for SDN is compelling in large data centers, and second, because I think data centers represent a microcosm that can be extrapolated to the metro network. So let's get down to business. In large data centers, there are some significant challenges. So first of all, there's an explosion of traffic resulting from a number of sources, especially video, mobile data, and big data, and much of this is sourced from data centers. So these effects, together with server virtualization, web applications, and the need to replicate vast amounts of data internally and between data centers, has led to large, dynamically changing traffic patterns and flows. The immediate result of this is an overloading of networks, and this causes increased latency and ultimately leads to degraded application performance. An alternate solution is to design the network for worst-case traffic. However, this leads to a significant increase in cost, and we're at a time where we know that revenue from customers is stagnant, so it's really not sustainable. The solution which really does offer some value is to be able to reconfigure the network on demand to put the capacity where it's needed most. And this results in a high-performance network that makes the best use of available resources. Looking at this another way, what you'll find in most data center networks today are fixed capacities with everything-to-everything connectivity. The connectivity basically doesn't scale to support the large data flows that we're talking about as they arise. So what's needed here is connectivity and capacity where it's actually required, and also the ability to deliver the bandwidth and the server resources needed by applications on demand. So on this slide, it isn't animated, so think of the connections on the right-hand side there, the colored connections between the servers and racks, as being moving and changing periodically as the traffic flows demand. This network reconfiguration can only be partially realized with traditional switching and routing solutions. So while they're suitable for short, bursty traffic, they typically can't support the switching of large data flows economically or with the low latency needed for many applications. So optical circuit switching complements this solution with the capability to economically reconfigure the network to support massive data flows with low latency and to scale as needed to 40 or 100 gigabits or even beyond that as the needs dictate. So what we end up with here is a hybrid packet circuit switch network without a means to control it, and this is where SDN comes to the rescue. So what we show here is the well-known multi-layer SDN model with the application, control, and infrastructure layers. The important point here is that the packet and optical circuit switches can all coexist together in the infrastructure layer with coordinated control from the upper layers. How we see this coming together today in the large data centers is a management plane and a control plane containing both packet and circuit elements. So the management plane creates and manages topologies and related configurations, and it also analyzes the various flows within the network in coordination with the photonic and routing control planes. Then the control planes orchestrate the topology-related configuration changes. So the photonic engine manages the topology changes across the optical layer, while the routing engine further manages the topology changes across the various routing engines running at the different top-of-rack switches. So before going further, I wanted to do a short level set on photonic switching or optical circuit switching, as it's sometimes known. So basically what it is and what it isn't. The first point is that it's entirely optical, so there's no OEO conversions here. Most photonic switching solutions use some form of 2D or 3D optical MEMS technology. In Calient's case, we use a 3D MEMS technology, which we fabricate in-house in Santa Barbara. The image on the upper right shows one plane of micromirrors which can be moved by voltages applied to electrodes to move the mirrors to any desired position. And to give an idea, of size, a chip containing 384 mirrors is approximately 1 square centimeter in area. The key benefits of an all-optical 3D MEMS approach are a few things: high capacity, low power compared with other switching solutions, very low latency, and the lowest cost per bit compared with typical traditional switching, routing, and OEO solutions. Now, these features are particularly well suited to the switching of large data flows. Let's look at a couple of use case examples of optical circuit switching in SDN in a large data center. So this diagram depicts a fairly typical modern data center with racks of servers organized into clusters and with edge routers connecting to the metro network. Clusters would typically be connected with layer 2 switching and layer 3 routing, and these are not shown here. To this, we've added a photonic switch fabric and an SDN management and control plane. In this use case, there are two specific top-of-rack switches which have a need for high capacity and also low latency, so for a link between them to support a specific data flow need. This is recognized by the SDN control and management plane, and the control plane instructs the photonic switch to add a direct optical interconnect between the two top-of-rack switches. So this executes and the optical path is set up supporting basically a massive data flow capability between the top-of-rack switches, and this with very low latency. This path can remain set up for as long as it's needed and then can be taken down and moved elsewhere. The any-to-any capabilities of the optical circuit switch really allows for a very large range of connectivity between clusters and racks within the data center. The next use case shows optical paths connected between the server clusters and the edge routers connecting to the metro network. The scenario here is that cluster 1 requires a step increase in bandwidth to the metro because of a time of day demand. It could be a morning load on an email server, for example. The second cluster isn't using as much bandwidth, and so based on the situation, the management and control planes can reallocate metro bandwidth between clusters as shown on the next slide. So later in the day, as other clusters experience the need for more metro bandwidth, the optical switch can be instructed to reallocate the optical pipe to another cluster as needed. Moving into the metro area, the applications are quite similar. Here we're talking about interconnecting cloud data centers and POPs, for instance, and some of the capabilities of optical circuit switching together with SDN here are first of all, rapid service provisioning and reconfiguration, and secondly, dynamic network optimization. So, for example, opening up high bandwidth to a specific site in a content distribution network while content is transferred, or for data replication between data centers. The benefit, as in the data center examples, is to be able to allocate the fiber capacity where it is most needed on demand. So basically to make the best use of these network investments. So let's look at a simple example. The image on this slide depicts a network of data centers or POPs interconnected over a metro fiber network. The connections would most likely be implemented as wavelengths on a fiber ring. And let's say at a particular time of day there is a need for additional fiber connectivity between data centers 1 and 2. So the SDN control plane, working together with the optical circuit switch, can reallocate capacity from other nodes to support the short-term demand. So now you can see that the capacity has been rerouted from other connections to increase that capacity between data centers 1 and 2. Similarly, at another time of day, there may be an overload between data centers 3 and 4, and the fiber links can be rerouted to support that need. Before SDN, this sort of reconfiguration on demand at the optical layer would have been virtually impossible. Finally, to recap, a virtualized optical layer enabled by SDN allows the data center and the metro networks to be reconfigured on demand to provide the capacity where it's most needed at any time. In the metro network, optical layer reconfiguration is particularly important for data replications and for web applications and big data, where very high bandwidth and low latency are required. Finally, virtually unlimited scalability and lowest cost per bit allows service providers to deliver increased bandwidth and new applications in the most cost-effective way.